So you're welcome back. The first thing we want to study now in this video is the Fourier cosine series. So if you remember the way I explained it in the class, I call your attention to the fact that f of x here is divine and is known to be an even function. So that is the condition, that is the most important thing there about Fourier cosine series, that f of x is an even function. So if that is acceptable, if you take note of that, then it's very easy for us to know that there will never be anything like Bn in the Fourier series. So let's take a look at the proof. So we are familiar with A naught before, and from here we can see clearly that we need to partition the interval. So here we have it from minus pi to 0 and from 0 to pi f of x. But remember the condition, f of x here is an even function. So the next line is that we use the fact that, look at this fact I explained to you earlier, that this is only true because we have f of x is an even function. So that is why minus pi to 0 of f of x dx will give us is 0 to pi f of x dx. The condition is that f of x is an even function. Okay, so if you put this condition out here, which is this expression, we put that fact there. And what is the fact? That this integral, this definite integral, will change to minus pi, will change to 0 to pi. So that is how we obtain this. So we change it. That's how we obtain this expression. So we obtain this expression, then we have it here because we now have two of them from 0 to pi, and that will give us 2 of integral f of x dx from 0 to pi. So if that's a 2, we cancel 2, then we have this. That is our 12.1. So what about an? An now, we use this expression that we've derived together before, which is this expression. So the next thing is that we change, we partition the interval, and look at this, from minus pi to pi, now change from minus pi to 0, then 0 to pi. Aha. So we still use the same condition again, that f of x here is an f of x here is an even function. So if it's an even function, then the partition of the integral will change to 0 to infinity. Aha. That is how we have this expression here. So if you put this in here, we see that this with minus pi to 0 we change to 0 to pi, and f of x cos nx. So that's exactly how we obtain this. So this and this will give us 2 of it. Then we have to be 2 over pi. So, but remember, we are considering the fact that f of x is an even function. So for the cosine series, for the Fourier cosine, you now see that what we have here is 2 over pi. But for normal Fourier series, what we have is 1 over pi. So that is that. So let's proceed again. So for our Bn, we have this expression, but I think we can know that since f of x is even, sine nx is odd, then the product will give us odd. And since it's odd, we know that here, minus pi to 0, this expression here, this one here, since the product is odd. Why is it odd? F of x is even, sine nx is odd, then even times odd will give us odd. And when we obtain that, we substitute that, is why we obtain this expression. Aha. Because from minus pi to 0, we now become minus of 0 to pi f of x sine nx. And the reason is because f of the product here, the product we have here is odd. So that is it. Then this and this we subtract, then we have it to be 0. So what am I trying to say now is that for cosine series, for Fourier cosine series, we have our Bn to be 0. But our An is this. This is our An. This is our An. So let's consider example number 1. We have this wavefront that we've solved, and clearly looking at the graph, we can see clearly that this graph represents an even function, because from minus pi over 2 to pi over 2, we could see the kind of symmetric we have here. Okay, So let's solve it together. So we have our expression here, which is for Fourier cosine series when Bn is what? Is 0. So our A naught is this, while our An is 2 over pi. Remember, this Fourier cosine series 2 over pi, and we all know how we obtain this 2 over pi. So then we partition the look at it now. So we have it from pi to 1, from 0 to pi. This is an even function. So this is from 0 to pi, which means I want to cover only from 0 to pi. From 0 to pi here. So from the graph, we need to first of all deal from 0 to pi over 2. Why? Look at it. From 0 to pi over 2, f of x is 4. Then from pi over 2 to pi, f of x is what? Is 0. You see that? From pi over 2 to pi, f of x is 0. But from 0 to pi over 2, f of x is what? Is 4. That's how we obtain this expression. So from 0 to pi over 2, 4. Then from pi over 2 to pi, we have a 2b 0. So let's undo it now. If you integrate this one, you have 0. If you integrate, so you have 4x. Then from 0 to pi over 2, then we have evaluate the upper and lower bound. Then we have our a naught to be 2. Then what about our an? We use the same approach again, but one thing is that after we use the expression for an, Fourier coefficient an, this one we are dealing with cosine, Fourier cosine series. So we use 0 to pi over 2, 4, which is f of x, times cos nx, then is 0, f of x times this one. So we do that, is 0 here, we cancel. So from here to here, it will cancel. Let me highlight it in red color. It will cancel because 0 times this will give us a. So then you only need to evaluate this definite integral here, then which will give us this. So if you substitute, you evaluate, you use the upper and lower bound, then you have this expression. So the point now is this: when sine 0 is 0, then if n is even, from this expression, if n is even, what we obtain is 0. But if n is 1, 5, and 9, what we obtain here is 1. That is for selected for a certain number of odd. And even if n is 3, 7, 1, 1, what we're going to have here is what is minus 1. So we put all this facts into consideration to give us as. Remember in the class I said that this one we can use approximate sign. Please let's take note of that. It's possible. It's even better. It's more perfect to use approximate sign. Okay. So let's go to Fourier sine series 2. Just like I've explained earlier, for this concept of Fourier sine series, the only condition is that f of x is odd. F of x is odd. So the statement is this: if f of x is divided over the interval, and that same f of x is an odd function, then Fourier series for sine for f of x contains only sine terms only. It contains sine terms only. So we prove it. It's similar to the first one, but it's just that we impose that condition. By the time we impose that condition, always remember this integral. This expression is very important. That will help us a lot. So we have it like that. So without wasting our time, let's solve an example. Look at this example 13.1. We can see this in this example that the function we are dealing with here is an odd function. So we don't need to waste our time finding a naught and an. We know clearly that that will give us 0, 0. We only need to deal with bn. So what are bn? We have it to be 2 over pi 0 to pi f of x sine nx. So if you do this, we look at it. We only need to deal with from 0 to pi. So that will give us 0 to pi sine nx. Then we evaluate the integral. Then we have this expression. But always remember this. I've said earlier in the class that cos 0 is 1. Meanwhile, cos n pi is minus 1 over n. So we need this expression. We substitute here. Then we have this. Then we have our Fourier sine series for this graph. So what we are trying to say now is that that graph, this one here, it can be represented by this. If you plot the graph here, to give you the same graph, but note this is approximate.